Okay, so again, my name's Anthony Hardman. This is my colleague, Leslie Bew. You can look at our credentials up there. Basically, I just want to convey that between the two of us, we've spent the majority of our careers looking at buildings across the life cycle. I spent the majority of my career looking at the new construction, integrated design side. She spent the bulk of her career looking at existing buildings and retrofit projects. So with that, I'll hand it over to Leslie.
Thank you, Anthony, for the introduction, and thank you all for coming. This seminar, titled Building Energy Performance, Bridging Expectations to Reality, is a case study analysis. We're looking at the root cause analysis of simulation and performance dissimilarity, pinpointing common disconnects. So what that really means is that we're aiming to provide some real-world situations and some experiences we have seen in the field to provide and pinpoint the common disconnects that lead to that energy performance gap. We're going to be looking at new construction projects as well as retrofit projects, and we want to make sure that customers and investors continue to have confidence in our energy and sustainability projects. The learning objectives covered during this presentation are as listed here, and the two main points are going to be explaining the 5 most common pitfalls, as well as discussing the 5 most important corrective measures that mirror those pitfalls. Although he's not presenting with us today, our friend and colleague Tom Reed, will you raise your hand, Tom, was our co-author on a paper of similar content that Anthony presented on Monday. And he helped provide the case study details and lent his expertise on the subject matter, research, and conclusions used in the paper and in this presentation. During this presentation, our discussions will follow this agenda. First, we'll briefly comment on how energy and sustainability have become a large part of today's HVAC and building projects, and how although it's been a theme in the past, it is now more prevalent than ever, and from all signs, it's here to stay. Then we'll describe what is meant by the energy performance gap and show you how it affects new construction and retrofit projects alike. We will also briefly discuss the typical energy project roles and process while describing the nuances and differentiate new construction from retrofit and ESCO projects. Then we'll introduce the 5 main project pitfalls or disconnects that lead to the performance gap. Finally, we'll discuss 6 case studies that each highlight multiple of those pitfalls, and then discuss the solution or potential solutions. And then we'll recap in the conclusion. Although we don't need to spend a lot of time on this part, it's important to note that some people view energy and sustainability concerns as a passing trend, as it once was. In order for any of the topics in the rest of this presentation to really matter long term, it's critical to understand that energy and sustainability concerns and trends are not going anywhere. We can be certain of this based on these main points. First is environmental responsibility. With every passing year, we develop greater understanding of how air quality affects our health and productivity, and that's reflected in a lot of our ASHRAE recommendations. And secondly, climate change is a hot button right now. Whether or not you agree with the politics, we're seeing effects from climate change discussions, including the movement towards emissions reductions and markets such as carbon credit shares. Besides the environment and health discussions, putting energy and sustainability on the forefront, there are also economic and financial considerations showing that it's important and growing in strength. This graph shows a 50-year trend of average U.S. electricity rates from an NREL technical report. Even though there are periods shown on the blue line that have minor rate decreases, the rates often adjust afterwards with rapid increases. The overall trend line shown in red demonstrates that the energy rates, electricity rates, have continued to rise. This source concludes that the average U.S. electricity rates have increased overall in the last 50 years by 3% per year. And as you can see, the line is getting steeper towards our end of the graph. Utility rate escalations also depend on other factors such as inflation. According to that same NREL report, this figure illustrates a hypothetical organization's utilities, operation, and maintenance budgets. There is a constant annual budget increase to account for the rising utility rates, general inflation, and equipment degradation. The more people have to spend to operate their buildings, obviously, the more they're going to care about energy saving strategies. In addition to the environmental and publicity drivers, as well as the economic and financial drivers, we see trends in population growth and energy demand that provide reasonable conclusions that saving resources will continue to be necessary. And the growth and longevity of energy and sustainability industry itself is evidence that it is here to stay. Here's a graph showing construction spending in blue overlaid with LEED registrations in purple. What is particularly noteworthy about this chart is that the green industry has continued to maintain popularity and success even during a down economy. Those dashed lines are commonly understood recession boundaries. Even though LEED certification has a cost associated with it, registrations have continued during the recession. In addition to LEED new construction, energy service companies, or ESCOs, have continued to grow despite a general downturn in the broader economy. This chart depicts ESCO industry revenues through 2006, and then shows the projections from 2007 to 2011, which represent an average annual growth of 26%, and the reality showed very impressive growth similar to that as well. Now Anthony will discuss the performance gap.
Thank you, Leslie. How many design engineers do we have in the room? Big hands. How many analysts, modelers do we have in the room? Well, that's a pretty good mix. I think there's more analysts here. Didn't expect that. All right, so what is the performance gap we're referring to, and why is it important, and what kind of data do we have on it? And more importantly, what can we derive from that data? So the first chart that we're going to look at here, I want to big picture highlight that this data is from the LEED new construction integrative design process. And so there's a couple of main takeaways. First, it's noteworthy that a data point on the dashed line indicates that our predictions equaled actual measured consumption. Data points above the line indicate that the building performed much better than was predicted. And then data points below the line indicate that the building is performing worse than predicted. So again, big picture is we see some scatter here, and there's been many other presentations that show this same trend from new construction processes, analysis processes. There's a couple of key things that I want to touch on that we don't really highlight later. We talked about it on our Monday paper session, but essentially one thing that we want to drive home is that even though we may have perfectly designed buildings, we can still see variation from expectations with data such as this. And so what we would advocate is that we take data such as this at our initial design meetings and really go to our building operators and owners' reps to say, look, things can still happen after the building has been turned over, and even throughout operations that can lead to malperformance. And obviously, we can infer that there is a cost risk associated with this deviation between where the point lies and where the dashed line is. Moving on, this is the same type of graph. Again, big picture. This looks at retrofit projects or the existing building stock. And the first thing that'll probably jump out at you is that there's no data points below the line here. So why is that? Is there a process that's fundamentally different? What can we take away from the existing building analysis process that helps us ensure that our predictions are more in line with reality. We can also use this, again, as that same sort of argument, again, to building owners to say that, again, the delta between the data point and that dashed line represents risk and cost. In the existing building scenario, it's a little bit different in that delta is more of a missed opportunity rather than just wasted revenue. So the missed opportunity is basically accounted for in that it means additional capital could have been spent to achieve more savings out of that project. And I won't spend a lot of time on this. This basically corroborates the previous slide, and the main takeaway is that 57% of a much larger data set of studies indicated that in retrofit applications, our predictions are more conservative. We're saving more than we predict. I'm not going to spend a lot of time on this slide. It's basically meant to convey that there are a lot of stakeholders and team members throughout either the new construction or the retrofit process. And the main takeaway that I want to convey is that it takes all of these members, every team member working together in concert to ensure that we have a well-performing building. On the flip side, it only takes one of these members to derail a project. So we're going to look at the approaches here for a minute. This is an attempt to represent sort of the best case scenario in a new construction process. It shows that as analysts, we're involved from the beginning at the basis of design, and we're working in parallel with designers and feeding back results to them as the design phases progress. And I say it's a best case scenario because there's probably many analysts in this room have experienced a situation where we're not brought in until after CDs have been released, at which point we're merely performing a verification function, and there's obviously limited value in that. So big picture, we start out at the beginning with a lot of alternatives, hopefully, that we're assessing to try to find the best ones. We have very little details, so the onus is upon us as analysts to make very good assumptions and try to understand what the critical nodes of these systems are, even if all you have is a basis of design document without any drawings to go with it. And hopefully we're coming up with a suite of results that we're feeding back into the design process to help our designers come up with the most efficient system possible. And so we iterate this process several times until at the very end we hope that we have all the detail we need. We're not making any assumptions, and we're getting the final answer that says, you're 20% better than code. So we're going to contrast that a little bit to the existing building analysis retrofit process. And so oftentimes this process starts with an energy concept being sold to a building owner. And then that gets handed off, in many cases, to an analyst who then looks at those alternatives, perhaps presents more. One key difference in this scenario is that the details are derived from existing conditions. We have the ability to go in there and really measure what's happening and observe that accurately. We come up with our results, and we'll package those in a way that's meaningful to the building owners. They then have some decisions to make. They can choose which option or options they want based on corporate goals. Maybe it's carbon emissions, maybe it's simply ROI or lowest first costs even. And once those decisions have been made, we as analysts, we feed those requirements to designers. So the role of consultant is almost switched in this scenario. And so the designers design according to analyst requirements. And then the biggest thing that you'll see is different is this results and verification function on the bottom right here. That is probably the biggest differentiator between the existing building process and the new construction process. So big takeaway, existing buildings, we have M&V afterwards, and analysts are more in the driver's seat dictating how to design for performance. Not going to spend a lot of time with this. So here's some of the pitfalls. Leslie and I will go over these in more case study detail later. But we oftentimes have team members who are underqualified for what the goals of the project are. Many times operators are not giving the support and training they need to operate the equipment as it's intended. Details refers more to design details and how we as engineers are specifying our equipment to operate. Installation errors can always happen. communication is always a challenge, not just between designers and analysts, but also between installers and designers. If the gap exists, at the very basic level, it means that a change happened in the field or in the design that wasn't communicated to an analyst. And then finally, accountability is, as we see, is more built into the existing building process, and that step is often missing from a new construction process, unless the designers have been contracted up front for M&V follow-on work. But I want to pick on us as engineers on the details section before, because when we went through this process, we saw some very troubling and glaring tendencies. As consultants, we've had the opportunity to work with many engineering firms, and some great and some less great. And one of the things that we see far too often are poorly written or merely absent sequences of operation. So we'll get this great complex system, and there's no control sequences to go along with it. And that's probably the most egregious example. Lesser examples include stock control sequences. Hey, we had this system in the last project, let's copy-paste it. That we see that, again, way too often. And then probably the least egregious example is scenarios where the controls simply have not been written or optimized to take full advantage of the equipment that's been installed. And I'm not stretching the truth here by saying this occurs a majority of the time, and it's not a rare instance. So we as engineers need to be doing a much better job in our quality control to ensure that we're actually looking at sequences early on and making sure that we're speaking to those very clearly in our drawings and our specifications. So we'll start with a couple of case studies here. One thing about problem, again, this discussion is discussing the problem of the gap between predicted and measured. So not necessarily the building problem. There may be a building problem, but that's not the problem that we're trying to address here. If there is a poor control sequence, we should still be able to reflect that in the analysis. So this first case study is a 18,000 square foot nature center that achieved LEED New Construction 2.0 Gold. It was built with groundwater source, water-to-air heat pumps, package units throughout the building, had a rooftop solar PV system, and it had a predicted EUI of 22. Upon building turnover, it was discovered that none of the second floor units were working. None of the other units had any problems whatsoever, but the second floor was constantly tripping off. Eventually, we found out that the corrected and measured EUI was 29. So what caused this? Well, we went back and saw that the pumps had been upsized at almost 3 times what was originally specified, and this was done because the water table was initially guessed to be 40 feet, when in fact it was more like 125 feet. So they had to triple that capacity to overcome the static head. So just to skip forward a little bit, when we went back and corrected for the pump upsizing, the accuracy was within 10% of actual. So what was the gap diagnosis here? We can start with incorrect design details or assumptions. I mean, obviously, if we're going to design this system, we would have an understanding that having that water table knowledge is pretty critical. I mean, nothing else is really going to work without that knowledge. And it also could have been a bad assumption. In any case, that could be attributed to a design error. But there's also poor communication here. At the very least, the installer should have communicated what that water table was to the design engineer. And from the design and engineer's perspective, when they did make this pump change after the fact, that change should have been communicated to an analyst so that could have been incorporated into follow-on results. None of that occurred. So incorrect design details, poor assumptions, poor communication. The second one is a dormitory case study in North Carolina. 75,000 square feet, achieved LEED NC 2.2 Silver, and it was tied into an existing campus steam and chilled water plant. Interestingly, again, for a dorm, they used an overhead VAV delivery system. It was a highly controlled, or had the ability to be a highly controlled building. They had operable windows, occupancy sensors, integrated BMS, and we predicted the EUI to be around 90. one of the first problems that we experienced, this project was completed in 2010. Last year, the campus or the university came back to us and said, our summertime heating is actually above what your wintertime predicted is. What's going on here? And so, that could be a problem. And they also saw that their domestic hot water usage was constantly increasing. It never had achieved a sort of steady state. And we saw that once we got their data, their actual EUI was 240. 3 times what we'd predicted, and certainly well beyond what you'd expect for any sort of multifamily or dorm type building. The good thing about the university is that they engaged us. They were cognizant of this data, even though there wasn't an official M&B contract. And universities tend to be good clients in that regard. They have more of a vested interest in what those operating costs are. So what was the cause? The big one you'll probably see here is that their BMS was taking the domestic hot water meter and was continually summing it rather than resetting it on a monthly basis, which for a dorm, as you can imagine, has a big contribution there. Some other things, higher usage. There were a lot of common areas that were allowed to be used by the students, the residents, more often, or a lot more often, and for more hours per day than were originally anticipated. Some other things, with the operable windows, there was no lockout system that turned the heating and cooling off while those windows were open. And perhaps the biggest thing, the engineers were great in that they worked with us from the beginning to really find what those optimum control sequences are. We did a lot of parametrics to give that information to them and really find the best balance there. And none of that, when we went back and looked at the BMS and the units, none of that was implemented. It's as though everything had been overwritten or was never there to begin with. So what's the gap diagnosis here? Installation, it was either there or perhaps the operators, at some point, either the control sequences that were specified were not programmed, or the operators merely overwrote those. So we can also look at that as being an underqualified team. Why did this occur? Did the controls contractors not have the ability to write the controls as they were specified? There was no verification by engineers specifically to go in after the fact to ensure that, again, their systems were designed according to their specifications. This is actually a good example of accountability, again, in that the university came back to us, they recognized a problem, and they got the engineers back on board, and they're working to correct the problem currently. So with that, I'll hand this back to Leslie to finish out our case studies.
All right. For the third case study, we're going to discuss a community center located in the mountains that received LEED points for some impressive design intentions. Once the building was operational and occupied, they determined that it wasn't performing as well as expected or as well as peers. A third-party energy team was being brought in then to narrow down what the potential problem spots were and to determine how to solve this problem. During the investigation, it was determined that the piping seemed that it was installed correctly and it was well insulated. The condensing boilers that were installed were operating optimally. The proper unoccupied setbacks and scheduling were implemented. And proper ventilation rates were being delivered. We weren't excessively ventilating. And the lighting and daylight harvesting system seemed to be appearing to work properly. So the next question was the building envelope. The building has a pitched roof with acoustic drop ceilings in most of the spaces, and bad insulation was laid above the drop ceilings. But after eliminating other possible contributors, the energy engineer noticed that the roof was visible through the recessed can lighting fixtures throughout the space. Apparently, after further investigation, holes it was noticed that holes were cut in the insulation to provide room for the fixtures and to prevent fire risk, but no insulation was ever laid back over it in proper fashion. This effectively created a bypass for warm air from the space to pass through the fixture into the uninsulated roof and through a bunch of the roof penetrations. Yeah, this picture obviously depicts a closed can fixture. Couldn't find the perfect picture here. It was an open can fixture, and so on the top there it was wide open, and you could see through to the ceiling. Either way, these type of can fixtures have vents in them to allow airflow so that they don't overheat and burn out your ballasts and bulbs, etc. So either way, you're going to get some heat transfer through it, which is why it's important to put the insulation over it. Without being a part of the design or installation process, we have to make assumptions about some of the likely disconnects. We could speculate on several causes for this problem. Most likely, the areas with the drop ceilings were modeled with the full insulation rating, but the effective rating, as you saw in the picture, was not. It was far less than it should have been. Design, schedule, and financial constraints could have caused designers and energy modelers to not properly document the installation strategy details. And without proper communication, the installers may assume the easiest and cheapest way to insulate rather than following the designer's intent. Inadequate oversight was apparent, and communication with the designer and owner's rep was lacking. A church in Denver with equipment so old it was barely operational is our fourth case study. The owners knew they needed new equipment, and after discussions with their chosen contractor, agreed that they would invest even more money to upgrade the equipment and install more energy efficient equipment than the standard like-for-like replacement. It was based on promised energy savings and life cycle cost projections. So obviously, if the systems, such as the boilers, the efficient boilers and chillers, and the direct digital controls building automation system, if they didn't perform as well as expected, then the owner would have just invested additional money with no return on investment. Close to the end of the project, the energy engineer was brought in to verify operation. None of the systems were installed quite right. They did provide heating and cooling, but would not achieve the savings originally projected. And the systems were having many problems as well, and the building operators didn't know what to do with it. In fact, at one point, they asked if we could remove the computer system and reinstall the non-programmable thermostats. No one was happy. One of the main problems was that the energy concept didn't match the submittal drawings, which didn't match the installation. So they were all going down different paths. The installer had apparently decided that because the submittal drawings were impossible to install, that they would go ahead and provide a workaround. But they weren't cognizant of the performance critical piping changes for the system. It was a two-pipe system that the boiler and the chiller were being swapped based on chiller and refrigeration guidelines in small spaces, and so therefore some of the piping had to be changed, and in addition, because they were high-efficient systems, condensing boilers, there needed to be more primary, secondary type piping, and a lot of that didn't happen. And this is just one of the examples of some of the drawings in part of this building. Exacerbating the problem was that the two-pipe changeover pneumatic valves were not replaced, after all, due to value engineering. So now the air compressor had to remain, and the valves left in place impacted the required fail-safe operation, resulting in additional costs to correct it anyway. Lastly, the controls contractor set up the hot water supply temperature to reset between 150 degrees and 180 degrees, which is great for a conventional boiler, but we're going to eliminate the savings potential in a condensing boiler application. Luckily, none of the problems lasted long. the analyst had first-hand knowledge of the existing system operation and therefore modeled it accordingly. During verification of the new system, the analyst noticed the valve and piping issues we discussed, and since those issues were caught, they were corrected. But if the installers had communicated the discrepancies prior to their workaround, they wouldn't have had to repipe it 3 times. If the development team had communicated to the analyst the proposed value engineering detail, the impacts could have been addressed at that point, and then it would have provided a less costly alternative solution. And lastly, the sequence of operation and improper set points were discovered by the analyst during verification, so the proper changes were made. Then additional training was provided to the customer and end users to explain the proper operation of condensing boiler systems as well as the other high-efficiency systems installed in this scope. In the end, this project was successful for the customer, but many of the problems and cost overruns could have been avoided by planning, more details, and more communication between the disciplines. In this project, the contractor was accountable to provide a turnkey energy performance solution in order to maintain their reputation and to maintain business with a long-term customer. Our 5th case study is about a community center in the Mid-Atlantic region that was designed to meet LEED Silver standards and has many great sustainability and energy features. Those exceptional efficiency and sustainability features were clearly goals of the project. Since the building ended up using much more energy than it expected, and even a lot more energy than a lot of its peers, after 2 years, the owners funded a retrocommissioning study to better understand the building's performance. They learned the hard way that green building design and energy-efficient equipment doesn't guarantee actual energy efficiency performance. Many deficiencies were then identified. Substantial gaps in the ductwork throughout the building were found, leading to short cycling of the air-conditioned air. Most of the costly supply air being produced was never making it to the occupied spaces. Also, the heat recovery wheels, a great addition for highly energy efficient systems, were controlled so poorly that they were actually contributing to additional energy waste. This great technology has many advantages, but if the controls are not implemented precisely and the system isn't installed correctly, then it certainly can impact the energy usage negatively. Not only was the operation of the heat recovery wheels incorrect, but the controls for the rest of the high-efficiency equipment were not operating the components of the system in any energy-efficient manner, so they were losing out on all of the potential benefits of installing higher-cost, higher-efficiency equipment. Again, here we point out that proper design has to include the details necessary to convey not only the equipment to be ordered, but also the proper installation and proper operation and control sequence to effectively operate these energy-efficient systems. That also helped the modeler not have to make assumptions as well. Highly qualified designers may have provided that detail, but then again, if the installers and future operators had no accountability to install it correctly and operate it as designed, then that may have been the issue, but we don't know for sure in this case. Whether it be an owner's rep or qualified commissioning agent, someone should have caught these mistakes during the installation, not 3 years later. As always, the maintenance and operations staff, whether that's the customer or a separate third-party contractor or service provider, must be properly trained on how the systems differ from traditional systems. Even with a lot of experience, installers and operators may not always understand the costly impacts to the long-term building operation. In this case, the study identified deficiencies that, after eventually being resolved, reduced the building's operating costs by $35,000 annually. Our 6th and final case study shows a high-end resort that spared no cost when designing for guest comfort and mountain appeal. Located at a high-end ski resort, everything is high quality except for the HVAC installation. In the first year it opened, there were still many systems that didn't even work correctly, and the energy waste was shameful. In the conference rooms, the temperatures were out of control, and guests weren't comfortable, and the energy bills were a lot higher than they had expected. The energy and mechanical service provider, which was not the original builder or contractor, noticed the issues as soon as they started providing maintenance and offered to help solve some of the problems. Observations indicated that the designers oversized the chiller and the boilers. The chiller couldn't even stay on. It couldn't stay on longer than its minimum on-time limit. It was having problems even during the hottest days of the summer. The equipment that was selected had very high efficiency ratings, and the system should have been able to run really well together, but the controls weren't installed well. And they didn't employ strategies that were actually necessary to achieve any of these energy savings and to operate this equipment as it should have been. Making things worse, the snow melt system, which keeps the sidewalks and street completely dry, was providing heat for the resort as well as the local municipality. The resort was to sell a portion of the heat that went to that municipality based on BTU meter readings monthly. However, the BTU meter had been installed on the wrong pipe, causing the resort to underbill the town by $90,000 per year for 2 whole years. Lastly, the incredible turnover of building staff in resort towns makes it extremely hard to find and keep qualified operators. And since the building engineers don't really have any accountability for the energy costs, but are rated based on comfort complaints and elimination of problems, they often don't have any real incentive to correctly diagnose and solve problems. They often may override the control system or manually adjust something permanently. A successful day for them is a day that they don't get comfort complaints. And who can blame them when they're not incentivized, they're overworked, underpaid, and understaffed? Qualified people need to be sought out, hired, trained, compensated fairly, and probably incentivized appropriately. In this case, the resort was able to spare almost no expense to create a high-end luxury resort. They try to be good stewards of the environment and do a good job protecting the recreation land around them. But the lack of qualified team members on this project hurt them more than can even be estimated. Paying slightly more first cost for the construction project, or for qualified commissioning agents, or for the right control solution, and for their building engineers would likely save them a lot of money each year. Even though the energy services provider implemented operational changes that saved over $200,000 per year, they're still stuck operating a mediocre HVAC system in an otherwise luxury resort. As you've seen in the previous 6 case studies and examples, the necessary solutions often mirror the same pitfalls. So let's summarize the possible solutions to each of those pitfalls that are listed here. One solution is that you need to make sure you hire the right team as an owner, as a general contractor, and you need to spend more time and money up front, possibly, to find those quality team members. They don't always cost more, but you need to make sure they're qualified. This is important when selecting the entire team, including the final operator. For instance, can a young child operate perform complex calculations on a really sophisticated computer? Or can an experienced engineer effectively design a new building with today's leading technologies with only a slide rule? Maybe. But wouldn't it be better to have the best equipment and the best qualified expert? The second solution builds on the first. Details are important. Just as Anthony mentioned, details are a big deal. They can and will change during the process, but they're still necessary. In new construction projects, we learn that the process takes many iterations between design and modeler to determine the best scope. And then in the field during construction, based on some roadblock or new detail that arises, they have to be changed. But those details need to be documented. And this takes time and costs money and isn't as easy as providing generic sequences and generic operation details or drawings. But that's what sets the experts apart from the average project team. Many of the pitfalls we see actually occur during installation, or at least that's when we're identifying these pitfalls, and it's first obvious. It's easier to identify a problem in person, looking around at a plant or improperly installed equipment, rather than on drawings, but it's also much costlier at that point. Not every drawing is perfect, I know, shocker, but the same install does not fit all solutions. So if an installer notices a problem, they shouldn't just take the design in their own hands. They should be accountable and communicate those issues back to the designer. And then those same designers need to communicate with the modeler so that everyone understands the energy impact of these alterations. Otherwise, it's no wonder that the prediction isn't going to meet the actual energy efficiency or performance. Finally, how do we make project teams more accountable for the energy savings that have been predicted? That goes back to every team member, as we discussed. But it also goes back to the design process, the goals, and the incentives. We've already discussed the small differences between typical new construction projects and existing building retrofit or ESCO projects. This leads to further discussion of the typical design bid build process versus the design build model and other integrated design. And while we can see that performance guarantees are one potential solution to the accountability problem, they aren't always a good fit for every project. We don't have enough time in this presentation to completely talk about all of the promise that proper integrated design and performance guarantees show. There are other ASHRAE tracks that focus on those topics further, but it's clear that improving accountability will require initiating creative changes to the traditional processes that many of us are accustomed to. During this presentation, we've discussed how energy and sustainability is not going away. And we can all recognize that there are often issues causing gaps and disconnects between the predicted or modeled energy savings and the actual reality of building performance. The gap can be caused by over-predicting the savings or by underperforming buildings. And that gap happens in both new construction and in retrofit projects, even those following LEED guidelines. And it doesn't matter if the project's large or small, direct contracted or performance contracted, the gap can still occur. So what steps can owners and architects and project teams take to avoid this performance gap? Those common pitfalls that we saw and were discussed in those 6 case studies direct us right to those solutions. Qualified team members are imperative. Specific details must be accurate and well documented. The installation team must be qualified and be provided understanding of the impacts of their actions on the long-term cost of operating those buildings. And communication must include any design or installation changes back to the modeler as well as proper documentation for the owner or operator. And the operators, whether on staff or third-party contracts, must be qualified and properly trained. Finally, if we want to eliminate the performance gaps, we must all realize that while buying high-efficiency equipment certainly looks good on paper, proper installation and operation of the system is more impactful to achieving real energy savings. Thank you.